Welcome to this quick tech video on advanced synthesis with Vivado. In this video, we will improve the performance of a design example by analyzing the synthesis results and perform RTL code optimizations. Then we will resynthesize the design with these changes to measure their impact. To quickly converge on improving the performance, it is important to make sure that the constraints are clean, and it is best to iterate in synthesis without pushing the design all the way through implementation until the timing results show positive slack or at least little negative slack. As a design example, we are going to use a video IP design. So here's Vivado with all the sources of the design, RTL and constraints already preloaded. We can quickly review the files in the hierarchy source window to make sure that everything is correct. Everything looks fine here. At this point, we want to take a look at the synthesis options that are used and make sure we go with the defaults as much as possible. File out limit should be kept I. -no LC helps with area in some cases. It could be a good option to try if it's clear that dual output LUTs are in the critical path of the design. In this video, we won't spend time reviewing the constraints as they are very simple for the design. We only have a 300 MHz clock constraint described through a create clock in SDC. Let's now run synthesis. The synthesis is completed. So we will now open the synthesizer design, since this is where we want to iterate to analyze the results. So let's give it a few seconds for Vivado to open the synthesized design. Here we go, the design is now open. On the left window, we are going to select the report timing summary and run the timing analysis. We will take the default option and simply run the analysis by clicking OK. Once the report comes, we are going to check path with a negative slack, and in this case, we have quite a few that are quite negative. At this point, and to get a better idea of what's going on, we will open the schematic viewer and study the most critical path by right-clicking on schematic. As we can already see here, the performance bottleneck is in a design block called data path. The bottleneck is related to operators that are implemented as gates or logic, which clearly isn't the best way to go about implementing operators such as multipliers and adders into a Xilinx FPGA. We can select all the objects that compose the critical path and see them highlighted in the netlist view as well. We can also cross-probe to the corresponding source code by right-clicking on the object and select Go to Source or F7. We can do this on multiple objects in the path just to confirm the origin of the performance bottleneck until we have enough evidence of the RTL that's involved and how to fix the critical path from there. Code changes have already been implemented, and I also ran timing analysis. Same as earlier, selecting the topmost critical path, and notice how the slack looks better, despite still being negative. I am jumping to the schematic by pressing the F4 key, which is quite a useful shortcut. Here's the most critical path. There's a DSP block in it, and we can link it back to the source by pressing F7 or just right-clicking on it, picking the Go to Source. Here we go. Now I can see the RTL source in which the multiplier was used, and I can verify if that's what I expected. I can go back to the schematic again and check out the other path in the design to understand better what type of path I am having and what's their criticality. What I also like to do is going to the Tools, Timing menu, selecting the histogram. The histogram is going to give us useful information because it's going to give us the number of paths per criticality, and it's going to show us how much margin we have for the rest of the design. So here I'm selecting the most critical bin, the one in red. I can check out how many paths belong to that bin. And I can also study if they're all the same or not. That gives me precious information as to what do I need to change next. Since I don't have that many critical paths in the design and the worst slack is about 250 picoseconds, I'm going to push this design to implementation. Here I already implemented the design, and similarly to what we did for the synthesized view, we are going to review the critical path by using the result from the report timing summary command. As expected, given the limited negative slack after synthesis, the design meets timing. Slack is positive. We generate a schematic for the most critical path. We see that it involves a multiplier, which is not a surprise since we knew from synthesis that they were timing critical in this design. To better understand multiplier performance, it is useful to check how pipelined they are, and this information is visible in the Properties window once the object is selected. The properties to check are ARUG or BRUG, then MRUG, and finally PRUG for the product side. When any of these are set to 1, it means that their associated register is used. Here we can see that only PRUG is being pipelined, and that gives us a good information if we ever wanted to push the design beyond the current 300 MHz we are getting.